Hello AP Chem. In this video we're going to talk about solving equilibrium problems. When you are solving equilibrium problems, it is very important that you follow a series of steps. Skipping these can lead to problems and then you receive fewer points on your AP exam. So you want to follow the steps in the order that they are given to you. So steps for solving equilibrium problems. The first step is that you want to write your balanced equation. So we've done a lot with equations and making sure they're balanced, but that is going to be your first step. If a chemical reaction occurs, you're going to work out the stoichiometry and then write a second equation for the equilibrium reaction. You always do the stoichiometry in moles first. The second step is to set up the equilibrium expression. So this is your K equals the products, concentration of your products divided by the concentration of your reactants. And then if you can't tell which way the reaction is going to shift, you're going to need to solve for Q. So if you only have reactants at the beginning and you don't have any products, you know the reaction is going to shift to the right or in the forward direction, so you wouldn't need to solve for Q. But if you have both reactants and products that are present, you're going to need to solve for Q to determine which way your reaction will shift at equilibrium. Then you're going to want to set up a RICE table. RICE is an acronym for reaction, initial, change, and then equilibrium. So it includes your reaction, the balanced equation, the initial concentrations, the changes in the concentration in terms of X, and final concentrations. And then the fifth step, you're going to substitute these final concentrations into the equilibrium expression and solve for X. And then 6, you want to check and make sure that your answer seems logical. So in this first example, it says at 700 Kelvin, carbon monoxide reacts with water to form carbon dioxide and hydrogen. We're given our equation. The equilibrium constant for this reaction is 5.10. So K is equal to 5.10. We want to consider an experiment in which 1 mole of carbon monoxide and 1 mole of water are mixed together in a 1 liter flask. You're going to calculate the concentrations of all species at equilibrium. So here is our equation, just copied from above. And now because our moles are in 1 liter, this means that this is going to be 1 molar, and this is also going to be 1 molar. Now you'll notice that carbon dioxide and hydrogen were not mentioned in the problem. So when you are not given a initial concentration for a species in your reaction, you're going to assume 0. So I plugged 0 in here for carbon dioxide and for hydrogen. So now, because I only have reactants to start this reaction with, I know that I have to shift forward and to the right. So what that means is that I'm going to remove some of my reactants and I'm going to add some products. Now, because this equation has ones for all of the coefficients, that means that my reactants are going to decrease by the same amount that my products are going to increase. So we can show this with the change as minus X for each of the reactants and then a plus X for each of the products. And then for the equilibrium, we're just going to basically put the initial and the change together. So for equilibrium for carbon monoxide, we have 1.00 minus X. For water, 1.00 minus X. And then for carbon dioxide, just X, and hydrogen, just X. So we have our rise table. I haven't written out what the K expression is, or the equilibrium expression, but that is going to be the concentration of our products multiplied by each other divided by the concentration of our reactants. So now I have my equilibrium expression, I have my rice table set up. Now I'm going to plug in this line, the equilibrium line. I'm going to plug this in to the equilibrium expression, and that's where we're going to solve for X. So KEQ is equal to X for carbon dioxide, X for hydrogen, divided by carbon monoxide, 1.00 minus X times 1.00 minus X. And our equilibrium constant is 5.10. So now I'm going to simplify this a little bit. We have, I'm going to put 5.10 over here, is equal to X squared divided by 1.00 minus X, and that is squared. So now we need to solve for X. This is something that is called a perfect square, which makes our life easy because the top and bottom are both squared, so it makes our life easier to solve for X. So I'm going to take the square root of both sides, and this gives us 2.26 is equal to X over 1.00 minus X, and then continuing to solve for X. So X is going to equal 0.693. So now that we know what X is, we know what the concentration of carbon dioxide is. And we also know this is equal to X, hydrogen's also equal to X. So we know these concentrations to be 0.693. Now for carbon monoxide and water, we got to do a little bit of solving for those. So this is 1.00 minus X, sub in the 0.693 there. So this is going to be equal to 0.307 for carbon monoxide and for water. So assume 0. So over there on the right, you have a text box, and you're going to assume 0 for substances with no amount given. And since all the coefficients are 1, the reactants decrease and the products increase by the same amount, which is X. I'm going to do the next 2 examples in a new video. Sorry, I changed my mind. I think I can get this next example done in the next 5 minutes. So phosphorus pentachloride gas decomposes to form chlorine gas and phosphorus trichloride gas. At a certain temperature, 2-liter in a 2-liter flask initially contained 0.298 moles of PCl3 and 0.00870 moles of PCl5. After the system had reached equilibrium, 0.00200 moles of gas were present. So we're given this, but it is in a 2-liter flask. So we need to find, well, first write your reaction. Your phosphorus pentachloride produces phosphorus trichloride and chlorine gas. But now, because we're in a 2-liter flask, we need to solve for the molarity to find the concentration initially. So 0.298 divided by 2 gives us 0.149. And then do the same thing for PCl5. Now we can plug that into our rice table. And now it does mention the number of moles for chlorine, but this is when it has reached equilibrium. So this is going to be in our E line of the rice table. So in this reaction, because we have no chlorine, we can't form the reactant, so we have to progress forward and to the right. So we're going to, oops. So that means that for our change, we are going to decrease by x here, and we are going to increase by x and increase by x. Now, for our equilibrium, 0.00435 minus x for PCl5, and then 0.149 plus x. So you're just adding the I and the C line together to get your equilibrium line. But for chlorine, normally we just put x there, but because we were given this moles in the problem, we can go ahead and say this is x, but 0.00200 moles divided by 2 liters is going to give us 0.00100. So I'm going to go ahead and say what this is equal to. So now I'm going to write my K expression. PCl3 times the concentration of chlorine divided by PCl5 concentration. So now, on the last problem, we had to solve for what x was, but notice we weren't given what our K value was in this. But because we know what x is, that means that we can also find the equilibrium concentrations for everything here. So this is going to be 0.149 plus 0.00100, which turns into 0.150. And then this is 0.00435 minus 0.00100. And so this, sorry, I'm going to squeeze it in over here, 0.00335. So now we can plug this in and we can calculate what our equilibrium constant is. So PCl3 is 0.150 times 0.001 divided by 0.00335, and that is going to give us 0.0448 is what our K constant.